So let's look at what happens when we do have lone pairs on the central atoms. Just makes it a little bit more complex. So in that case, the molecular geometry is not equal to the electron pair geometry. Because remember, the molecular geometry depends on where the atoms are. And if we have an electron pair that is a lone pair, it's still repelling other electron pairs, but it's not an atom. So let's look at an example. If we look at the Lewis dot structure for sulfur dioxide, we find it has a steric number of 3. It has 2 atoms and a lone pair. Now this is not a trigonal planar molecule because the molecular geometry just depends on where oxygen, sulfur, and oxygen are. Just depends on where the atoms are. So if we look over here at the ball and stick model, we can see a clearer picture of what the molecular geometry is for sulfur dioxide. And we could call this V shape, upside down V, but bent is the typical word that's used. So when you have 3 atoms in a molecule, it can either be linear, if the steric number is 2, or it can be bent, if the steric number is not 2. And it's actually more complicated than that, but because we're only going up to steric number 4, those are going to be our rules. So if we look at what the bond angle would be, we still look at the bond angles due to the steric number of 3, and so this would be approximately 120 degrees. Now one of the things we need to keep in mind is that when we're thinking about bond angles, lone pairs are not tethered down by another nuclei. So what I mean by that is if we look at these 2 bonding electrons between sulfur and oxygen, they're being held in place by two different nuclei, the nucleus of sulfur and the nucleus of oxygen, and that is tethering those electrons in place. A lone pair, on the other hand, is held only by one nucleus, and I'm focusing on the nucleus because that's where the positive charge is that holds those electrons, that holds on to those electrons. So lone pairs are what we call fluffy. They take up a lot of room, and so therefore they repel with a little bit more force than bonding electrons. So lone pair to lone pair would have the greatest repulsion. Lone pair and bonding pair would have the next amount of repulsion. Bonding pair and bonding pair have the least amount of repulsion, and multiple bonds are going to repel more than single bonds because there are more electrons in that bond. So if we look at what the bond angle would be here in sulfur dioxide, to be absolutely correct, we would say less than 120 because of the presence of that lone pair, which is fluffy and repels more and pushes these 2 bonding electron pairs closer together. Now let's look at lone pairs when our steric number is 4. If we have no lone pairs on our central atom and our steric number is 4, then the molecule has a tetrahedral geometry. If we have a steric number of 4 and 1 lone pair, the electron pairs are still going to be oriented in a tetrahedral fashion because the lone pair and the bonding pairs are still going to repel one another. However, the molecular geometry will not be tetrahedral because I don't have 4 atoms bonded to my central atom. I only have 3. So when we have a steric number of 4 and 1 lone pair, the geometry of our molecule is known as trigonal pyramid. It's called trigonal because there are 3 bonds here, 3 atoms here, and it's pyramid because it's not in a plane. These bond angles are a little bit less than 109.5, and so a molecular model of a trigonal pyramid of a molecule with steric number 4 and 1 lone pair looks sort of like a tripod. It would stick up like a pyramid rather than be planar with a steric number 3. So if we look at our bond angle, tetrahedral bond angles are 109.5. There's 1 lone pair, which again is big and fluffy, so our bond angles are going to be less than 109.5. And in actuality, when we measure the bond angles in ammonia, which is what this molecule is, we find that they're 107, which makes sense, less than 109.5. And I just want to point out that the bond angles are going to decrease as the number of lone pairs on the central atom increases. So let's look at the last situation of when we have a steric number equal to 4 and we have 2 lone pairs. So here's our Lewis dot structure of water. We see that oxygen has a steric number of 4 because there are 2 atoms attached to it and 2 lone pairs. Now this atom has 3 atoms in it. What did I just say? This molecule has 3 atoms in it. Anytime we have a molecule with 3 atoms, it can either be linear or it can be bent. So in this case, the shape of water is bent. However, the bond angles are going to be different than a bent molecule that has a steric number of 3. So our 4 electron pairs are going to orient themselves to be as far apart as possible. Our 4 electron pairs are going to be in a tetrahedral arrangement. However, the molecule geometry, the molecular geometry, depends only on where the atoms are. So what is the bond angle going to be? Well, it's going to be less than 109.5 and even smaller than the bond angle in ammonia, because ammonia only had 1 lone pair. And we see that when we actually determine the bond angle in water, it turns out to be 104.5. So we see that that is smaller than 107. Now, I don't expect you to memorize the bond angles for water or for ammonia, but I do expect you to know the bond angles for tetrahedrally arranged electron pairs, which is 109.5. And you should know that if there are 2 lone pairs in the central atom, the bond angles are going to be smaller than if there's only 1 lone pair on the central atom.